Welcome back to Chemistry 4300. In this video we're going to continue Chapter 1 and we're going to start out with concepts of work, power, and kinetic energy. Now, when an external force acts on a particle and causes a displacement, that force is doing work on the particle. And we can calculate the work that it does through this equation here. So in this expression, we're taking the force vector and we're taking the dot product of that force vector with the displacement vector, the distance that the particle moves under the action of that force. And then we integrate from the initial position to the final position, and this gives us a scalar quantity called the work. Now, the work is a quantity which has a dimensionality of energy, and the SI unit for that is going to be the joule. We can take the work and take the derivative of the work with respect to time, and we get another quantity that's important. It's called the power. So if I take my expression for the differential work, so the inside here, F dot dr, and I divide it by dt, I can rearrange this expression to have the dot product of the force vector with the derivative of the position vector, and that becomes, of course, the velocity vector. So the power can be calculated as the dot product of the force vector and the velocity vector. And of course, the SI unit for power is the watt. Now let's continue on with that expression and see how we can get the work energy theorem. So starting with the power being equal to the dot product of the force and the velocity, I'm going to use Newton's second law, which is force is equals mass times acceleration. I'm going to replace acceleration with the derivative of the velocity with respect to time and substitute that in for the force. And now I have this expression here. I've made that substitution, and I'm going to expand out this dot product. And expanding that out in terms of the components of the velocity vector gives me this expression here for the x, y, and z parts. This expression here, turns out, you can get by taking the derivative with respect to time of this expression. So you may look at this for a bit. You might be able to work this out in your head. If not, I'm sure you can work it out pretty quickly at home. But just go ahead and try taking the derivative and seeing that this term goes to that term goes to that, and that one goes to that. So the reason we did this, of course, is you recognize that these are all the x, y, and z components of the kinetic energy. Now, if I recognize that these guys squared added up together is just the square of the magnitude of the velocity vector, then I can just simplify this into this expression. Of course, we identify that as the kinetic energy. So what we've shown is that the rate of change of the work is the rate of change of the kinetic energy, which I'm writing down as K. Okay. So that means that any work that's done on a particle is transformed into the kinetic energy of the particle. So this is what's called the work energy theorem. The work done by the net force acting on the particle is equal to the change in energy of the change in kinetic energy of the particle. Now, in the last slide here, what I want to look at is the total kinetic energy for our system of particles. And again, we want to think about this in terms of center mass system. So I'm going to write out the kinetic energy as 1/2 mv squared, but now you can see the velocity is just the rate of change of the position vector with respect to time squared. And now I'm going to go back and use my equation for writing out. I'll go back a couple slides here to remind you, using the position vector in my coordinate system as now the center of mass vector plus the position relative to the center of mass vector. And if I go back to this definition and I do that substitution with a little bit of algebra later, we're going to find that the kinetic energy can be divided up into a term that's associated with the kinetic energy associated with the center of mass. And then there's the term here, which is the kinetic energy associated with the rotation about the center of mass. So this will be important too, because when we talk about the rotational energy, we can take this term here and we can just sort of, if we think about our system in terms of the defining origin correctly, then we can think about it in the origin, with the origin defined correctly, we can take the center of mass kinetic energy and sort of throw it out of the problem, and we can just focus on the kinetic energy associated with rotation about the center of mass. Next, we're going to look at the work energy theorem with a subset of forces that are called conservative forces. A conservative force is a force that, when it acts on a particle, it depends only on the particle's position. So it doesn't depend on the particle's velocity or time or any other variable. Now, an important property of conservative forces is that the work done by conservative force is identical for all paths between 2 points. That means that this integral can evaluate simply to the difference between 2 quantities here, 2 scalar quantities. And the way I've written this is negative v for R2 minus v of R1. And this quantity has a name. We call this the potential energy. So the way this is written, this potential energy, this is what's called a scalar field. It's a physical quantity that can have any have different values at different points in space and time. So this is a result of our force being conservative and depending only on the particle's position. If I take the work-energy theorem for conservative forces, then I can write what we know, that the work being the difference in the kinetic energy, and now I can also know that it's equal to the difference in the potential energy with this negative sign here, and I can rearrange that and I get this expression here, that the sum of the kinetic and potential energy at the first position is equal to the sum of kinetic energy at the second position. So those combinations, those sums have to be equal to each other. And we're going to define that as equal to the total mechanical energy when a particle is moving between 2 positions by a conservative force. Now, I'm going to leave it up to you to prove that when only conservative forces act on the system, this total mechanical energy will be constant. It will be independent of time. Now, this result that we just saw also implies that we can calculate from this scalar field, this potential energy function, we can calculate the force vector. And that's done by taking the gradient of this function and then the negative of that. So the gradient function, which you may not remember, is just simply taking the partial derivative with respect to x and multiplying it times the unit vector along x, same for along y, and the same for along z. If I apply that to the potential energy function in Cartesian coordinates, then it would look something like this. Then I'd have the dv dx, dv dy, dv dz, all multiplied by the corresponding unit vectors. And what this here shows is gives us the direction of the greatest increase of the potential energy function in space. So in a 3-dimensional field, this is the direction, the gradient is the direction where the potential increases the most steeply. Now the force is going to be the negative of that, so that's going to be the direction that the force is going to push the particle. So it's a lot easier to see this in 1D. So let's look at this a little more closely. Here I've plotted some arbitrary potential function. I plot the potential as a function of position here. And what we see is that this function changes as a function of x. And there are points where the function has a 0 slope. So right here, right here, right here, and right here. So these points where the slope of the potential is 0 are the points where the force is going to be equal to 0. And what I've done below is I've plotted the force, which is the negative derivative of this, as a function of position here. And now you can see there's a 0 here. So you can see that where this slope is equal to 0, the force is equal to 0. Now, when you have a minimum like this in the potential energy function, then you can see that if you're on either side of this function, that the force will be pushing you back towards that stable equilibrium point. So what we'll see is that if I'm over here, for example, then the force will be positive and it'll be pushing me towards positive quantities. If I'm over here, the force is negative and it'll push me towards negative x. So if I'm in this region here, the force will always be pushing me towards this stable equilibrium point. Now conversely, if I'm at a maximum, like here, I still have a 0 slope, so there's no force exactly at this maximum. But if I'm on either side of this, see, the behavior is different. So you can see that if I'm on this side, the force is positive, it's going to push me towards positive values, and you can see that we're going to move away from that equilibrium point. That's what's called an unstable equilibrium point. Similarly, if I'm on the other side here, then the force is negative, and it's going to push me towards negative values, so we're going to be pushed, again, away from that equilibrium point. So this is what's called an unstable equilibrium point, and that's a stable equilibrium point. Now, additionally, you can see that if the total energy of the system, the kinetic plus potential energy, is, say, less than E2 but greater than E1, then you can see that if my particle was in this region here, I wouldn't have enough energy to get past this unstable equilibrium point, and I would be trapped in this region. So I couldn't get past here. Any energy above this point here, I do not have. My potential kinetic energy can't exceed that value. So you can see that I'm going to be trapped over here if I only have an energy that's between E1 and E2. On the other hand, if I'm on this side, then you can see that I'm not going to be able to get over this hump, but I will be able to get over this hump over here. So that means that if I'm on this side, I'm actually free to move out beyond this end of this plot here to other values of higher values of x. Now another subset of forces are a set called central forces. So the way central forces work is that they are defined so that they act radially out from some force center. So you can write this, if we took our force vector and we wrote it in terms of spherical coordinates, so you're used to writing in unit vectors in terms of Cartesian, but you could, if you wanted to switch to spherical coordinates, you could define these spherical unit vectors. And when you write your force in terms of spherical unit vectors, then it can be written in a form like this if it's a central force. So if it's a central force, then you just have a function of just the radius vector times the unit vector along r. If your central force is additionally conservative, then that means it must be spherically symmetric. So that means instead of being a function of the radius vector, it becomes just the function of the radius, how far the distance you are from the force center. So this is what happens if you have a conservative central force. And this is really convenient because then we'll find later in the course that a lot of problems with conservative central forces that we'll be dealing with can be easily transformed into one-dimensional problems, even though they start out as three-dimensional problems. Okay, now next we're just going to look at some sort of fundamental forces of nature now that we've sort of understood the general behaviors of forces, and just so to remind you of what those are that we're going to be dealing with. Now, we're not going to be dealing with gravitational force in this course because we're going to be working on a very small scale, but just to sort of calibrate you here, this is Newton's universal law for gravitation. And here's the expression for the force. This is also a central conservative force, and this is the expression for the force. G is the gravitational constant, and lowercase m and uppercase m are the two masses that are being attracted to each other. Now, another force that we're going to be dealing with often in this class is Coulomb law, and this is also a conservative central force. And this is a force where we have a force of attraction between two charges, so it can be either attractive or repulsion, actually, repulsive. And so the force is given by this expression here. So little q, large q are the two charges here, and these are the radius, the vectors, the distance vectors for those two charges. And this is Coulomb's law. And then just to be for completeness, we'll write down the magnetic force. This is the force between, say, two loops of wire carrying currents. So if there are currents flowing these two loops of wire, then there'll be a magnetic force between them. And you can calculate that magnetic force through this expression here. Now this is a little more challenging to evaluate, but generally it's understood relatively easy. There's the current flowing in loop 1, and then this is the segment dl1, and we're going to integrate over the whole loop here. And then here is the dot product with the current flowing in loop 2, integrated over each segment here, dl2, and then here is the two distance vectors between the two loops. And what's interesting is that magnetic forces are not conservative forces. Okay, I think that's it for this video. In the next video, we're going to look at equations of motions in terms of kinetic and potential energy.